Hello, Mr. Baina here, and for this episode, we will be talking about scalar quantity and vector quantities. So what's the difference between scalar quantity and vector quantity? The physical quantities are, number one is the scalar quantity. So what is a scalar quantity? A scalar quantity is a quantity that only has a magnitude or scale. Another name for scale is dimension. As an example to the scale are, we have the scale of mass or the magnitude of mass or the dimension of mass and the dimension of time or the scale of time. So this is a weighing scale, although it's called weighing scale, but it only measures the mass of an object. So this is an example of a scalar quantity. Another one is time. Time is another type of scalar quantity that is considered to be scalar because unlike vector, vector has a direction and you cannot add direction to time. So time therefore is a scalar quantity. Another example of a scalar quantity is distance. So there is a big difference between distance from a displacement. And distance is an example again of a scalar quantity. So what is the difference between distance and displacement? So this is an example of the difference between a displacement. A displacement is just simply a straight line or a straight path, but this one is called the vector quantity, whereas the distance is the actual path of the object that is really traveling. But for example, if this is the object traveling using the actual path, which is called the distance, the actual displacement position from this point to this point is actually displacement, and this one is called the vector quantity, while distance is the scalar quantity. Now if we are going to divide the value of the distance by the time, we will be able to get a new formula which is called speed. So speed is also another type of a scalar quantity. The vector quantity equivalent for speed is velocity. For now, we will consider speed and we will discover and determine the concept what speed is. So again, the formula for speed is actually distance over time, not displacement. So since this is distance over time, distance is a scalar quantity, therefore speed is a scalar quantity. It has no concern with its direction. So we have a problem in here to illustrate my point about scalar quantity, specifically speed. So I'm using a book called Shom's Outline for this problem. A runner makes one lap. When we say one lap, this is just a complete revolution in an oval. And let us say that the entire distance the person is traveling is 200 meters. So a 200-meter track, and he completed his one lap within 25 seconds only. Now the question, what were the runner's, letter A, average speed, and letter B, average velocity? But we will not answer average velocity for now because we will tackle this one later in the vector quantity. So for letter A, what is the runner's average speed? And from the definition is that speed is equal to distance traveled, which is 200 meters to complete the entire lap. Then the time taken is 25 seconds, so 200 meters divided by 25 seconds, the answer or the average speed of our runner is 8 meters per second. This time we are going to now look into the concept of vector quantity. So what's the difference really between a vector quantity from a scalar quantity? So the only difference between a vector quantity from a scalar quantity is that for a vector quantity, it has both having a magnitude or a scale and at the same time a direction. An example for a vector quantity is force. So why do you think that force has a direction? We will look at that in the next slide. Now in figure 1, there are two persons who is pushing the box. The first person is applying 40 Newton force and the other person is applying 30 Newton force. The direction of the force is going to the east, and the direction also of the other person is also going to the east, so that when their forces are added together, 40 newtons and 30 newtons both are going to the east, will deliver a net force of 70 newtons. So this is the concept why force is a vector quantity, because it has something to do, aside from the magnitude of 40 newtons and 30 newtons, it has something to do with the direction, which is all going to the east, and then all of their forces can be added. And that is an example of a dimension, which is the scale 70 newtons, and the direction, which is going to the east. In figure 2 is another type of scenario, because person 1, which is pushing the 40 newton going to the east, is actually opposed by another person who is pushing the box in the opposite direction. That is again having the 30 newtons going to the, instead of east, the opposite is west. So therefore 40 newtons going to the east minus 30 newtons going to the west, the net force actually generated is only 10 newtons, and that is obviously going to the east. And so this is another example wherein you can understand the concept of a vector quantity, and this is actually the magnitude or the scale, but the direction is obviously going to the east. Therefore this is a vector quantity. And the last image is that the person 1 is again still continuing pushing the box 40 newtons going to the east, but this time person 2 is again pushing the box at 30 newtons, which is the dimension, but this time it's going to the north, or we can also make use of, aside from north, to denote it with positive y, because vertical is usually denoted with y. So positive y going to the north. If it's going to the south, it is negative y. And our direction for going to the east can be positive x, while the direction going, for example in this case, going to the west, therefore that can be denoted as negative x. But in this case, it is actually a component method, which we can solve this one later on using the Pythagorean theorem that I am going to explain in the later of this slide. So another example for a vector quantity, because a while ago we were talking about distance for a scalar quantity, and that is also equivalent to displacement for vector quantity. And we are going to again look at the example, the definition between a displacement from a distance, because displacement is associated with vector quantity while distance is associated with scalar quantity. So again, displacement is just simply a straight line that is not the actual path of the traveling object, but that is the actual initial and the actual final path of the traveling object. But the actual distance actually that was followed by the real object's path is called the distance or the total distance. But this distance again is associated with only the scalar quantity, because it doesn't mind of the direction wherever the path is traveling. But the actual displacement is the position 1 where it originally started and the final position where it ends. This is the concern of the vector quantity. That's why displacement is very different from a distance. So displacement basically is the result of a straight line between the initial position and the final position. And so a while ago we were able to solve the letter A of this problem of that same runner that is traveling in one lap, that is about 200-meter track, in a time of 25 seconds, and we were able to determine the average speed by the total distance traveled by the runner, which is 200 meters, the entire complete set of the lap in just 25 seconds, and that is resulting to 8 meters per second of speed or average speed of that runner. But letter B, when we are asked now for um, the actually we are now asked for the average velocity, and remember that the average velocity is actually not the distance traveled but the displacement over time. And since the runner started from this point and he ends again running up to that point, the same place, meaning to say there is a total distance traveled but there is no displacement because the displacement is back to where the runner starts from running. Therefore the displacement is 0 meters divided by the time, which is 25 seconds, and therefore the velocity of the runner is actually 0, but the runner has a speed of 8 meters per second, but it has no velocity. And so I hope that this concept provides you now the understanding of the difference between speed as the scalar quantity while velocity as the vector quantity. So since it has something to do with the direction, the runner has no velocity but it has a speed. And so if we further continue, displacement is actually when we are going to divide displacement by time, that will end up with velocity. And remember that in scalar quantity, distance divided by time is actually speed, while in vector quantity, displacement divided by time is velocity. But here's another bonus, because velocity that will be divided by time is called acceleration. So again, velocity is actually the change in position over the change in time, and the change in position is that from point 1 to point 2. That's actually the displacement. So velocity is basically displacement over time. So in this problem, we are again going to illustrate the difference between displacement and distance. And for this case, we have P1, which is the initial position where the object is actually traveling into the total path distance while it ends up to P2. So definitely the straight path is from P1 to P2, and that will be our displacement. And supposing that our P2 is 5 meters from P1, therefore the displacement is actually 5 meters. Supposing that this is east and this is south, therefore it is 5 meters south of east. So that's the distance and direction. And to get velocity is simply displacement over time, and our displacement is actually 5 meters, and supposing the time to reach from P1 to P2 traveling the actual path is actually equal to 2 seconds. Therefore 5 meters divided by 2 seconds is equal to 2.5 meters per second, and it is moving towards south of east, meaning south reference to east. And again, as I have mentioned already, that velocity, when it is divided by time, the value there or the new unit there is called acceleration. So what is acceleration? And there are several representations of acceleration. Here is one way to illustrate acceleration, and acceleration is equal to velocity over time. Example, what is the acceleration of a car from 0 meter per second, which is a velocity already, to 5.2 meters per second, which is another velocity in 1 second. And so the formula for acceleration is A is equal to the initial, or I'm sorry, the final velocity minus the initial velocity divided by the time. And so our acceleration therefore is that the final velocity, which is 5.2 meters per second, minus 0, because the car is actually stopping at this time, which is there is no acceleration, or I'm sorry, there is no velocity yet, divided by the time, which is 1 second. So the change of acceleration, which is 5.2 meters per second minus 0 over 1 second, will result to an acceleration of 5.2 meter per second. And since the second divided by second will become 5.2 meters per second squared, and therefore the final acceleration is now equal to 5.2 meters per second squared. And remember that we know this is an acceleration because there is a second squared in the unit of acceleration. Here is another way of looking at acceleration due to gravity, because our planet is actually pulling any object towards the center of it. And for example, another heavenly body such as the moon is also pulling a particular gravitational pull of that body towards the center of it. But the only thing is that they are having two different pull of gravitational values. And so we will be looking at that now. So the acceleration of a body moving only under the force of gravity is called g. So g simply means acceleration due to gravity. The gravitational or free fall acceleration, which is directed vertically towards the Earth, actually towards the center of the Earth. For the Earth, our gravitational pull is actually 9.81 meter per second squared. And you know this is acceleration because the unit has a second squared. That is having an equivalent value of 32.2 in terms of the metric system, which is feet per second squared. Now, the value varies slightly from place to place here on Earth, but in the moon, we have an actually significant difference from 9.81 meter per second squared here on Earth, but in the moon is actually 1.6 meter per second squared. And according to the second law of motion, which we are going to tackle later on, the second law of motion of Einstein is that the force actually, or the force or the weight generated by any person of having the same mass, whether it's on Earth or in the moon, will be computed by the following formula, which is equal to the mass of the person multiplied by the gravitational acceleration of that place like moon or Earth. And so to illustrate my point, here I have here the formula again. Weight is equal to acceleration due to gravity, which is g. And remember that the force or the weight of the person is actually equal to mass times acceleration. And since this is acted due to the force of the gravity, we will change the symbol letter A into g, meaning to say that this time it is just simply the gravitational pull, which is 9.81 meter per second squared. For example, the weight of the person is 560 newtons. We will be able to determine the actual mass of that person by the formula force is equal to mass times gravity. And so if we are going to divide 560 by 9.81, we will be able to get the mass of that person here on Earth, which is 57 kilograms. Now, what if this person is placed on the moon, and so the person will only have a weight there that is equivalent to 92.34, but the formula is still the same. Force or weight is equal to mass times gravity, but this time we will be using the gravity of the moon, which is 1.6 meter per second square. And so we will still be able to determine the same mass of that person, because the mass of the person, which is 57 kilogram, is always constant here on Earth and constant in the moon. But the only difference is that they have different gravitational pull. That's why when you are here on Earth, you are a little bit heavier of about 560 Newton compared to 92.34 only in the moon. That is because that's the attraction of the gravitational pull on Earth, which is 9.81 and 1.6 on the moon. Now we are going to try to solve for this problem. This is again coming from the Shom's outline book. And so there is a problem here. An object starts from rest, meaning to say that the object has actually zero velocity. So with a constant acceleration of 8 meters per second squared. Now we know this is an acceleration because it has a second squared at the unit along a straight line. So we are asked to find letter A, what will be the speed at the end of 5 seconds. So definitely we are now given the time, and letter B, the average speed for the 5-second interval after, and letter C, the distance traveled in the 5 seconds. So we are interested in the motion for the first 5 seconds. So here, take the direction of the motion to be positive this time, and we are traveling in an x direction, because remember, this is a vector quantity, so we have to reconsider the direction, assuming that our direction is in the direction of positive x. That is why our s here, or the distance, is equal to x. Now we know that the initial velocity, because it is from rest, the initial velocity is 0, but from rest until 5 seconds later, and it will already generate an acceleration of 8 meters per second squared. Now, because the motion is uniformly accelerated, now there is a specific formula for this one, for a uniformly accelerated. Now remember, I'm using here A because this is not the gravitational pull that is directed towards the earth, but it's an acceleration really of a moving object, and this moving object is called in a uniformly accelerating moving object. And so the formula for finding the velocity of that object is equal to the initial velocity. And remember that the initial velocity is 0 plus the acceleration multiplied by the time. We can cancel time because remember that acceleration is in seconds squared, multiplied by the time. That will cancel out, so this becomes at becomes actually the velocity this time. And so this is a standard formula that you don't have to worry about. This is already given, and so we will now replace all the different units of the formula that is present in here. Now remember that our initial velocity is at rest, therefore there is no velocity there, so we can write that there 0, while the acceleration is already 8.0 meter per second squared, and the time is actually 5 seconds. And so we will be multiplying 8 times 5, but we will cancel out the second there. So now that becomes 40 meter per second. So therefore the value is actually 40 meter per second. And so we are actually answering letter A, and letter A is actually just to find the speed after 5 seconds. And so this is the speed that is generated, so 40 meters per second. Now letter B, the average speed. Now again, letter B is that the average speed for the 5-second interval, and so we can again be making use of the velocity, which is the average velocity. And how the formula is utilized in here is that the initial velocity plus the final velocity divided by 2, and again the initial velocity is 0 because you know this is coming from rest, and the final velocity is 40 because we are now able to generate what is the final velocity in the first problem, which is to find the velocity after 5 seconds. And so that will be divided by 2, so 40 divided by 2 will only be 20 meters per second. And finally, to solve for letter C, what will be the total distance traveled after 5 seconds? And we will be able to use another type of formula, which I am going to introduce all of this later in the next slide. But for this purpose, I will just introduce to you that we will be using the formula X, which is the distance, the vertical distance, or the horizontal, the horizontal distance, because the vertical distance is denoted by Y, but this is X, so this is referring to the horizontal distance, which is equal to the initial velocity multiplied by the time plus 1/2 times the acceleration times t square. And so if we are going to replace this, again the initial velocity is 0 because it is coming from rest, plus 1/2, then multiplied by our acceleration, which is already given, 8.00 meter per second squared, multiplied by the time square, and the time is 5.00 seconds. Then you will raise that to the power of 2 or square, and the answer will be 100 meters. Therefore, x is equal to v or the initial velocity and then multiplied by the time, or the average velocity rather multiplied by the time. And the average velocity is, we have 20 meters per second multiplied by 5, which is the time, and that will again resolve to the same answer, which is 100 meters. So we can both make use of this formula or this formula. These are all standard formula, so you don't have to worry of this one. And so, by the way, vector quantity can be added to produce what we call the resultant vector. So what is a resultant vector? So this is a concept of a resultant vector. We have one vector over here. We also have another vector over here. And so the resultant of these two vectors is actually this final vector, which is this one. And so we will still be digging that out, how this can be added together. So in finding for the resultant vector, there are actually two methods in finding for the resultant vector. The first method is called the graphical method.
Hello, how are you? And welcome to our lesson in mechanics. And this is the addition of vector using the tip to tail, tip to tail method. All right, now sometimes this is called the head to tail method. Sometimes they call it the closed polygon method. Okay, so tip to tail method. Now this time we will be making use of an arrow to illustrate our point. So I'm going to draw a straight line. This is just a horizontal line, and that is our arrowhead, and this will be labeled as the tip or the head. All right, the head. So opposite to the head, which is that one, that will be labeled as, of course, the tail of our vector. Now this is an arrow that represents a vector. How about the body? The length of the body is actually called our measurement of the scale, which is the dimension. Remember that a vector quantity is a scale or a scalar quantity plus a direction. So that's what makes it vector quantity. So that's our dimension. I'm sorry that I'm using a different color pencils. I'm sorry, a pen, but you cannot clearly see the difference of the color in my video. So to give you an example, all right, to give you an example, okay, we are going to draw, all right, draw we are going to draw a vector quantity. So draw the vector. Now let's think of a number, about 50, yeah, 50 meters, comma, the direction will be 30 degrees north from east. All right, so that's also called north of east. All right, okay, that's it. So in other words, from the east, okay, from the east, you are going to measure 30 degrees going to, okay, Yes, going to north. Right. Okay, just an example. So we will be drawing first the orientation line. We have the y-axis, okay, and on top of the y-axis will be our north, okay, that's also positive y, and below is our south, negative y, and we'll find the center. I think that's it. We will draw a horizontal line which is called the x-axis right there, and of course that's the east orientation and the west orientation. Okay, now we have to consider the 30 degrees, okay, northeast. Now in our protractor, you have to make use of the center of the protractor from the edge. Okay, that's it. Where you start to draw the angle, where you start to locate the angle, that's 10 degrees, 20, 30 degrees. Let's mark 30 degrees. All right. Now, usually you are going to make use, okay, from the center to that one, that is where you will locate the angle. Now, usually you will be making use of pencil here, but in our case, I will just be drawing using a pen for you to see clearly. So this is not yet the dimension, and then we will be considering a scale system for our vector quantity. Okay, because later on we will be measuring the certain vectors together using the tip-to-tail method. So our scale here is 1 cm is to 10 meters. So that is 1 cm or 10 millimeters in my ruler. And that's it. That's how wide 1 cm is. That's equivalent to 10 meters. All right, that's it. 10 meters. Okay, so we will transfer that down, and remember we are going to locate the 50 meters, so that will be equivalent to 5 centimeters or 50 millimeters in my ruler. Now we will measure. That's 10, 20, 30, 40, and 50. Okay, let's mark that one. That will be our arrow head or the tip of our vector. Okay, actually that's the tip of our vector. And then let us now make the solid line from the origin, from the tail to the tip. All right, so that will be our vector, and we will put the angle. Now north of east. Now take a look at that, from east going north, east going to north. All right, that is 30 degrees. All right, 30 degrees. Now we will be writing down the vector. We will label the vector as v1 or vector 1, which is 50 meters, comma 30 degrees northeast. Okay, that's it. Now let's have an activity on this, and this time you will be making use of your materials. Okay, so activity number 1. Okay, number 1, for activity number 1, you are going to draw the following. Following. Right, that's an abbreviation for following. Okay, number 1, and let's have 75 meters. Okay, comma, the angle is 45 degrees. Okay, very special angle, north of east. All right, number 2, about 50, yes, 50 meters, 30 degrees south west. Okay, from from west going south. All right. Number 3 will be 30 meters, okay, east, right? Just east. And then number 4, we will have maybe 80. Yes, 80 meters, 70 degrees. Okay, going north from east. And the last number, which is number 5 or vector 5, will be 35 meters, 20 degrees south of east. Okay. And with the help of our ruler, we can sketch out a line. Okay. And then from there, we will measure the 50 meters. Again, we will be using the scale 1 cm equals 10 meters. Okay. So since this is 50 meters, we will now be measuring around 50 meters in our scale, and that should be equal to 5 centimeters, because 1 centimeter represents 10 meters. So that is 5 centimeters or 50 millimeters. So that should not be a problem. Make the solid line that will represent vector number 1. And of course, the angle again is 30 degrees going north. That's the symbol, going to north. Alright. Then the next vector is 30 meters east. So this will now be the characteristic of the tip to tail. So the tip of the first vector will be connected to the tail of the second vector, which is vector number 2. And vector number 2 has no y component or no component along the north axis. Therefore, that's only directly going to east, right? So we will be measuring the dimension of vector number 2, which is 30 meters. That will be only equivalent to 3 centimeters or 30 millimeters. And that's the 30th meter representation. So in this plot, so we'll plot that out, solid line. So that will be our vector number 2. And this time, vector number 3 is 50 meters going to north. So this time, there is no x-axis or x component. So we'll just be drawing a soft line going to north. Alright. And then we will measure 50 meters. So let's plot that out. Alright, we will be counting 1, 2, 3, 4, 5. So that is 5 meters. So again, the tail of the last vector is connected to the previous vector tip. So the tip of the second vector is connected to the tail of the last vector. So that's vector 2 and that's vector 3. So this is again the tip to tail method in adding vector quantity. And this time we will be connecting the tip of the last vector to the tail of the first vector. This is the way to get your resultant vector. Alright, so we will draw a solid line up to there. So that should be the new direction of the resultant vector represented by V sub r. Okay. So now we will measure the dimension of V sub r. So let us count 3, 8, 9, 10. But there is more than 10, so 6, 7. So that is 10.7. Okay, 10.7 centimeters. Right, that's it. So remember, our scaling is 1 centimeter is equal to 10 centimeters, or is equal to 10 meters. So that is also equal to 1 centimeter in every 10 meters, which is equal to the measurement, which is 10.7 centimeters in our ruler. That should be equal to the value of vector r in meters. Or you can also rewrite it as vector r value is equal to 10.7 centimeters. That will be equivalent to our scale, which is 10 meters over 1 centimeter. Right? Okay. So I want to remove the 10.7 centimeters there. I can just simply remove that by multiplying it to the same value, 10.7 centimeter. But because there's an equality sign, I'm also going to write that in the other side of the equation. Cancel the centimeter unit, and I will cancel it out because 10.7 by itself is just 1, so that will become VR. And on the other side of the equation, that will become 10 meter times 10.7 centimeters over 1 centimeter. Okay, we can cancel later the centimeter like that. Cancel that out. So we will be left by a meter. So probably 10 times 10.7, that will be equal to 107 meters. No more centimeter. Okay? So let me get my calculator and check that out. Okay. All right. Now this time, I would like to know the angle generated by the new resultant vector. So we will be counting that. 0 degree, 10, 20, okay, 30, 40, and half of that, 45. Yes, so that's 45 degrees. So 45 degrees, okay, from, okay, that's the trace of the new, let's trace the new angle. That's 45 degrees. Okay, that's the new angle. Alright. Okay, that's the 45 degrees from east to north. Going north from east. Okay. So rewriting the final answer, vector resultant is equal to 107 meters, 45 degrees east to north or north of east. So that's it, guys. That's how you will be able to solve the tip to tail method. Thanks for watching.
And the next method is parallelogram method, which I am going to explain to you. The parallelogram method requires trigonometric function and Pythagorean theorem. So first of all, we are going to understand what trigonometric function is. Now, for example, if this is a triangle, this is the angle theta. Opposite to the angle theta is called the opposite. And adjacent, or the line beside next to the theta angle, is called the adjacent, while the longest line in this right triangle is called hypotenuse. And these are the formula in solving for this trigonometric function. If you are going to look for the opposite and hypotenuse is given, you can make use of the formula sine theta. But if you want to look for the value of the adjacent and the hypotenuse again is given, you will be able to use cosine theta. But for example, if the opposite and adjacent are already given, you can solve for the theta by making use of the shift or the opposite of tangent theta. Now here we are going to apply the problem. For example, our hypotenuse is 7 meters and our theta is 30 degrees. We do not know how much our opposite is. We also do not know how much our adjacent is. And again, if I would like to solve for the opposite, I am going to use sine theta. And my sine theta here is 30 degrees. And so sine theta is equal to opposite over hypotenuse. So that sine our theta is 30 degrees, opposite over 7 meters. And our opposite is actually can be solved using the 7 meters times sine theta. So this is actually being transposed. So 7 meters, which is a divisor, when it is transposed to the other side, it becomes multiplication to sine theta. So 7 meters times sine 30, opposite is now equal to 3.178 meters. So this one is actually 3.178 meters. And how about the adjacent? For the adjacent, you can make use of this formula. Cosine theta is equal to 30 degrees again, and cosine theta by this formula is adjacent over hypotenuse. And cosine 30, which is our cosine theta, is equal to adjacent over 7 meters. And to solve for adjacent, that is 7 meters, which is our hypotenuse, multiplied to cosine theta, which is 30 degrees. And by the use of our calculator, adjacent will now becomes equal to 6.257 meters, or we will reduce that into 6.24. So our 3 is now raised to 4 because the next value is actually more than 5. So 6.24 meters. Now in this problem, supposing that our opposite is 3.178 meters and our adjacent is 6.257. So what will be our theta? And in this case, we will be using tangent theta, which is opposite over adjacent. And so we will replace the formula. Tangent theta is equal to opposite over adjacent, and our opposite again is 3.178 divided by adjacent, which is 6.237 meters. And so the value will become 0.5095. And so with your calculator, you just have to shift tangent theta of this value, which is 0.5095. The value again goes back to our original theta, which is 30 degrees. And so now we are going to apply the trigonometric function in solving for the component method. And here I have already plotted the coordinate line. So all the values that is going up, the vertical line is called north. That is also equivalent to positive y. And the values going to the right is belonging to the direction of east. That is also equivalent to positive x. While the negative value of our vertical line, which is negative y, that is also equal to south. And going to the west, that is negative x, that is also in the direction of west. Now I have here a problem. We have vector 1 that is equal to 7 meters going east, and vector 2 that is 5 meters going north. all you have to do is to find the resultant vector when we are going to add vector 1 with vector 2. So how is that going to happen? I will show you the solution. So in this case, I am now putting the value of vector 1, which is 7 meters, going to the east. So assuming that this is 7 meters and this is vector 1 and it is going to the east. And our vector 2 is 5 meters going to the north. So we are going to attach, let us assume or just estimate that vector 2 is equal to 5 meters, but that is going to the north. Meaning to say vector 1 is in the x direction, positive x, and our vector 2 is in the positive y direction, which is north. So actually in the component method, instead of putting the value of the next vector in the original tip, this is actually a head to tail method. And so the first vector, which is 7 meters east, will be laying in the x direction, and on the tip of our vector 1 we will attach vector 2, which is going to the north. And so this is now the new setup of our illustration, and we will be able now to find the tangent, because tangent theta is just simply opposite over adjacent, and remember that our opposite is already 5 meters and our adjacent is already 7 meters. So meaning to say we will now be able to determine the actual theta of this vector. So basically we are going to use tangent theta, which is equal to opposite over adjacent, and our opposite is actually 5 meters north, and our adjacent is 7 meters east. Therefore 5 meters divided by 7, the value of that one is 0.71428571429. And therefore if we would like to take the angle or the theta for this one, all you have to do is to shift the tangent theta of this value, and our angle theta is equal to 39.49 degrees. So this time I'm going to introduce you to the new concept, which is the using of the Pythagorean theorem. And Pythagorean theorem is that if you have A and you have B and you have the side C, you can solve either C, A, or B using this formula: a squared plus b squared is equal to c squared. And we will now be applying that one here, because actually the resultant vector is from the tip of the first vector to from the tail of the first vector to the tip of the last vector, and this is actually the actual resultant vector. And this will be our C, this will be our A, and this will be our B. So how much is the dimension of that one? This we will be using the formula Pythagorean theorem. So again, our A is vector 2, and our B is vector 1, and our C is VR, or the resultant vector. And so we are going to make use of this formula: a squared plus b squared equals c squared, and our a squared is actually 5 meters raised to the power of 2, and our b squared is 7 meters now raised to the power of 2, is equal to our c, which is v sub r, that is raised also to the power of 2. And so our c, which is also v sub r, is actually equal to 5 meters square plus 7 meters square. So again, c is equal to v sub r is equal to 5 meters square plus 7 meters square. And remember that our v sub r is also raised to the power of 2, but when we are going to transpose the power of 2 to the other side, it becomes a square root. And so v sub r, the square root of 5 meters raised to the power of 2 plus 7 meters raised to the power of 2, the v sub r there is equal now to 8.602 meters. So again, our c, or the v sub r, or the resultant vector, is now equal to 8.602 meters. So how are we going to write this one as the final answer? It is so simple. V sub r therefore is equal to the value of our c, or v sub r, is 8.602 meters, comma, and our theta is 39.49. And remember, we are now in the direction of going to the east, and that is opening towards the north, so that's 39.49 north of east. This is now the final answer for the components of the two vectors. So that's all for the concept of vector and scalar quantity, and thank you very much.